Okay. All right. Welcome everybody to the East Valley Astronomy Club online meeting for December. The agenda, we'll do the usual welcome and introductions, but we'll talk a little bit about do's or do. Yeah, it's that time of year again. A little bit about the conjunction coming up. I know we probably all know about it. We're all following it, but I'll just give a slide talking a little bit about it. Again, our club news. Our member presentation is by one of our own members, Claude. And our main presentation is by Ed, the circumgalactic medium, or the turbulence and the halos of galaxies. So I will get right on to it. So as usual, welcome guys. Live long and prosper. Guys, 2020 is almost over. Yes, finally. Oh, I think I'll go to sleep for a couple weeks just to make 2021 get over here quicker. You know, my gosh, what a horrible year, huh? So, introductions. I throw this screen up every meeting. Here's the people, the officers, the administrators, the board of directors. Here's the ones who are actually running the club. They're keeping it going. And during these tough times, it's been tough to do, but we've turned negatives into positives. One of them is these online meetings. And so I'll give just a moment here to go on down, let you read the names. The names should be familiar to you all now. But down at the bottom left there, the most important member of the club is you, the members. You're the ones who actually make this club. These people up here really just run the club, but all the members actually are the most important part of it. So because of that, you got to pay your dues. So it's time to renew your dues. Everybody's dues expires on the 31st. You're a life member, and you just do yearly. Well, the yearly memberships expire at the end of this month. So don't let that Christmas Grinch steal your membership. It's only $30, $35 for a family. What a bargain, right? They can be paid online via the club website. So remember the club website, East Valley Astronomy Club Online.org, has a lot of information on what's going on. Click on the membership link. It has the form to fill out, where to send your dues. It can either be done over the internet, PayPal is available, or you can drop it in the mail with a check. So fork over your membership dues, eh? Support your club. Jupiter and Saturn conjunction. Again, everybody knows what's going on with this. I just looked out there today. They're getting pretty close, but also they're getting pretty low on the horizon. So December 21st is when they will appear to be their closest. And of course, you know, what's happening here off to the lower left is, here's the conjunction. They're still, half a billion miles apart, something like that. But it looks like that they're in line from how we are viewing them. So on December 21st, they get the closest. Make sure you get out there and view it. Get your binoculars out there, your telescope, and see what it looks like. Remember, here's all the things that are happening. If you miss it and you don't get out there and view it, hey, don't worry about it. We can look at it again in the year 2080. So club news, or rather the club olds. All the EVAC personal contact events still remain canceled. And so anything that's public, we have canceled. Still do not know when we're going to get back together. However, next year is promising, that's for sure, with all that's going on lately. So sometime next year, we hope that we're back with some sort of public in-person type events, and making sure that any kind of safety regulations or things like that are complied with. But 2021 certainly looks better. So more reason to get those dues paid up, because next year we're going to be doing some new things. Member presentations, just like what you'll see today. Claude Haynes, our member, who's also our Greco manager, is going to give us a member presentation. If you want to give one, and please, I encourage everyone to give a 10-minute presentation. And let me know. Just use that link on our website, the EVAC president. Let me know. And if you need a practice run, Tom and I will schedule one where you can do a practice run before the meeting. We'll do whatever it takes to make sure that your member presentation is successful. And of course, these meetings are recorded just like they all have been. Again, go into the website, and in our meetings page, just go to December, give us a day to get it on, and click on it, and it will come on up. So the next EVAC meeting is Friday the 15th of January, same time, 7:30 p.m., and we'll be into the year 2021. Yay. The main presentation will be by Dr. Travis Rector, and it'll be about the color composite images by professional observatories. Now, those who are little deep into astrophotography will start stacking different colors, showing the different frequencies of objects. And well, the professional observatories do that too. And the reasons that they do that and the results will be in that presentation by Travis. So member presentation right now, Claude Haynes will give his Requiem for Arecibo. How sad. So Claude, I am going to give the screen to you.
You're muted, Claude.
How you doing?
There we go. And hopefully you see a slide with a very large observatory. Tonight we're giving a Requiem for Arecibo. As many of you are aware, it has suffered a major collapse and is no longer functioning. It's a unique non-optical telescope in a natural depression. If you are not scientifically inclined, you may remember it from such wonderful films as GoldenEye with 007 racing around the observatory.
Claude, I'm not seeing your screen.
Aha, well, let's try this again. Let's go back. Where are we at? As it, shh. Let's try one more time. Now do you see?
That's
There we
better.
go, yes.
Aha, now, see, technology is wonderful. All right, so we're having a Requiem for Arecibo. You may remember it from such wonderful movies as GoldenEye or Contact with Jodie Foster, who seems much more excited by the night sky than her fellow researcher is. He seems to be more excited about her. And if you remember, the observatory was a radio observatory. There was a large gantry, 900 tons, with the antenna array. And the antenna array could swing on this arm here or in this circle, so it could be placed for optimum reception with the dish down below. And it was supported by these three large towers, very much like a suspension bridge. Now, unfortunately, this is the view that many of us have seen of Arecibo. The first cable snap was in August, another in November, and then finally, on December the 1st, early in the morning, there was a catastrophic collapse. The gantry fell, the catwalk, the tops of the towers snapped off. It was a pretty cataclysmic event and the end and demise of the observatory. The National Science Foundation had already stated that because of the severe damage to the first two cable snaps, that the observatory was going to be demolished, that it was not safe for them to continue. But nature took over with a pretty spectacular collapse. Now, in 2010, I was fortunate enough to visit Arecibo. Like most vacationers, you end up with bad pictures taken by people you hand cameras to. I was on a Caribbean cruise, and part of the cruise was classes on board ship, and we got to tour Arecibo, and it was really great fun. It was somewhat like stepping back in time, though. This is one of the original control consoles. The tile work is original from 1963 when the observatory opened. You can see their accommodation here for handicap accessibility in the building. The various dials and rheostats and gauges to run things. The observatory facility itself also is pretty small. It was cram-packed, full of equipment racks, air conditioning ducts to keep things cool. They had upgraded, so it was not, not in the ancient mode. They were digital, lots of computers, so they were operating as a state-of-the-art facility. And it was interesting, as I walked around, most of the equipment racks had tags that said Cornell University. Now, if we were having a live meeting, I would ask the question, how many of you can name a famous astronomer who spent most of his career at Cornell? And you would say Carl Sagan. Edwin Hubble had the Hooker and the Hale telescopes. Sagan had Arecibo, and this is one telescope that he used for a lot of his astronomical work, a lot of the science that he did because of the connection of Arecibo with Cornell. Also, there was a connection with SETI, and this is one of the equipment racks for SETI. The search for extraterrestrial radio emissions from nearby developed intelligent populations, or SERENDIP. Astronomers love stars, but I think they love acronyms more. So this was the SETI computer that was just taking the raw feed from the observatory, and if they were able to get a signal from ET, then they were able to know what had happened. One of the features of the cruise and the tour was that we actually got to go down under the dome itself, and so we were all just having a lot of fun being underneath the array. Yes, we spent almost all of our time staring up, taking pictures. This is Angel, one of the administrators. And as you can see, it's kind of fun down there. This is the opening in the center. You can see the grid of the panels, and on the outside edge, there's an extension that kind of helps shape the signal into this parabolic dome. Underneath the observatory, you can see these concrete piers, which were used to tension the panels to keep the parabolic shape. And it was kind of a storage yard for antennas. These are fixed length antennas that would go on the gantry next to the Gregorian dome. And you were able to change out the antenna for different runs if you were trying to do specific research within a specific bandwidth. This is a concrete tower. You can see the huge suspension cables that were used to keep up the gantry, very much like a suspension bridge. The antenna was completed in 1963. It was 305 meters or 1,000 feet across as a dish. With the collapse of Arecibo, currently the largest radio telescope is in China. It's called FAST, or Heavenly Eye. And they've recently announced it opened up in 2016. It's 500 meters. It cost about $171 million to construct, but they also spent over $200 million on infrastructure and relocation of people to create a 35-mile exclusion zone to keep radio interference out from the area. They've also recently announced that they will be open to more international cooperation with the loss of Arecibo. remains to be seen, but that is now the largest radio telescope. And you can see from the positioning near Guangzhou that it is fairly southern in China and near the latitude of Arecibo in Puerto Rico. And that is kind of important. The research that's done by this type of radio receiver is fairly fixed because it's in a natural depression. The the dish itself can't really move. In Arecibo, the gantry platform that we talked about where you could rotate the antennas, that let you change the direction a little bit. And so you could gain plus or minus a few degrees of latitude for your research. In the Chinese telescope, where you saw those fixed piers with keeping tension on the panels, they actually have actuators so they can change slightly the shape of the dish itself to change the parameters of the dish if it's required. But there's a major difference between the two telescopes. And the fact is, Arecibo was not just a radio receiver, it was a radio and radar. So the FAST telescope receives signals. The Arecibo telescope was able to generate radar signals, so it could do a lot more specific research in a lot of areas. This is a sign at the top of the hill going down toward the dish, and shielded vehicles do not pass this point with a red light. And here's a picture I picked up from the internet. This is a guy with his snowshoe Crocs walking along the dome. And I'll put this delicately not to insult anyone who's an animal rights individual, but this is like an open air microwave oven. And if anything happened to accidentally fly across the dome during the transmission or during one of their runs, they did not survive. So this is a kind of an interesting area, but it was, as a radar facility, they could generate a huge amount of power to send signals out into space. Here's a list of some of the things that are the top achievements of Arecibo over the year. Clocking the speed of the Crab Nebula pulsar. They were able to send a lot of radar information and get great radio signals from pulsars. That pulsars spin up by pulling material from their companions. This was the basis in 1974 of a Nobel Prize for Richard Hulsa and Joseph Taylor to be able to show that specific case where pulsar is stealing material from its companion. Ice at the North Pole of Mercury and the rotation of Mercury. That was a big mystery. It turned out to be 59 days instead of the 88 days for its annular or one orbit. So it proved that Mercury was not in a tidally locked situation, but it has a really slow rotation. Also, maps of the surface of Venus. This was done in conjunction with probes from NASA to study Venus. The radar was able to pierce the clouds and give some great images of the volcanoes and the surface terrain of Venus. Mapping the shape and spin of asteroids is a very important one. And phoning ET, we're going to talk specifically about those two in a minute, but you remember the time when Arecibo was used to send a message out into space. Recently, the study of repeating radio bursts. And in that study of pulsars came an idea that gravitational waves could also be detected. And that early research from Arecibo led to the creation of the Gravitational Wave Observatory that recently picked up the echo from merging black holes. And finally, planets around pulsars. I can't think of a worse neighborhood to live in next to a huge source of energy, but the radar determined planets around some pulsars as well. If we talk about phoning ET, this is a message that was sent. It was sent in 1974. It was at 3 trillion watts sent out toward M13. It looks like a video game graphic from the period. So if Pac-Man happens to pick up the signal, maybe he'll be able to interpret it no bets on whether or not anyone else would be able to figure it out, but it's possible. The photo here, though, on the right is much more important. It's because the radar capability allowed Arecibo to determine the shape and spin of asteroids. Cleopatra is one of the ones that's most famous. It's kind of the dog bone shape that was discovered by Arecibo. In 2020 alone, they had characterized 67 asteroids before the collapse of the antenna. The site still has a 12-meter radio telescope, very similar to the U of A telescope, sub-millimeter telescope up on Mount Graham for long baseline interferometry. And they also have a LIDAR observatory. So they're still doing work, but the loss of the large dish has certainly impeded that. But they are going to be spending years still going and sifting through and data mining the previous data to see what they can find. This is one of my slides, and I'm not trying to be overly critical, but if you read the top of the sign, and you can notice that the letters have worn a bit. It opened in 1963. It always operated on a shoestring budget. The initial funding included Air Force study of the ionosphere. So back in the 60s, it was very helpful in doing detailed analysis of the ionosphere, of radio propagation. That was very helpful to us as we developed some very sophisticated technologies at the start of the space race. However, by 2000, the National Science Foundation had cut the budget by 15%, and they had announced that further cuts were going to take place in the next 4 years out. In 2011, a new consortium management structure was created. Cornell left or took a minor position, and other universities stepped in. And finally, in 2019, the University of Central Florida assumed management of the observatory itself. One of the issues that you have with science research is it's expensive. Every 10 years, there's a decadal survey where universities and NASA and other institutions beg the National Science Foundation and government and other places for grants. This is one of those years, so all of the grant proposals are in. The announcements will be made in 2021 of future scientific research that gets funded. But if you think about it, they're funding the new, and oftentimes the funding of existing facilities is forced to be sacrificed to pay for those new funds. And there's some things that are close to home on that. Kitt Peak was funded by that decadal survey to build a national observatory there in the 60s. But the 4-meter telescope, the Mayall and the McMass Solar Telescope are now barely operational because of funding issues. Think of Mount Wilson, Yerkes Observatory. They're basically historical sites now, not active research sites. Something else that's painful when you look at the devastation, though, of the dome, of the dish and the gantry that's fallen. Every year, over 50,000 school children would come and visit the observatory. And additionally, 50,000 tourists each year would come. This is a huge educational and economic loss for the island of Puerto Rico. And it's been through a lot. I'm not sure what caused the collapse. There's been a lot of speculation. It could be deferred maintenance. It could be that there was some serious damage from some of the hurricanes that had blown through that just wasn't visible. It is an active seismic area, and there are earthquakes that have happened in the area. So it's certainly possible that there could have been damage that was hidden from view and that we wouldn't have been able to fix it. But it would be interesting to look back and see if we had a little more funding for maintenance, would Arecibo have been able to be saved? Talking about new technology, there is an idea and a proposal that we should have a radio telescope on the far side of the moon. This would be created with robots who could stretch the wires across the craters. And this has two advantages. One, it helps us to be able to study things below 30 megahertz. That's the frequency at 30 megahertz and below that's blocked by the Earth's atmosphere, and it would be isolated from Earth's based radio interference. Now, some of you, I'm sure, are already ahead of me. We happen to have a very large gaping hole in the North Arizona desert. And so if we needed to have a feasibility study for a replacement for Arecibo, something that might take place in the moon, hey, I think we're all up for it. So in closing, I would like to wish Requiem Aeternum for Arecibo. We want to thank you for your service to astronomy and earth science, but you're going to be missed. So Gordon, back to you. If I can figure out how to do that. It's up
Okay.
here. I'm going to pause sharing. I'm going to stop sharing. Okay.
There we go.
Hopefully we're
Yeah.
back.
Thank you, Claude. Very good example of a member presentation. So anyone that had gone on another trip, or maybe you went to talk about your impression of conjunction, come on, give a member presentation. Oh, by the way, the conjunction too, ASU is planning on an online event. And well, if it clouds over, which chances are always that some astronomy event is going to be clouded over. But I'm sure there's a lot of other online sites that are going to be having live views of it. So you might even want to do that anyway, is check around. That's all I had. So what I'll do is I'll hand it over to Tom Mosden for our main presentation.
Thanks, Gordon. I might comment on Claude's suggestion of using meteor crater. They might get a little touchy there, as if you see a rusty tin can and it's 49 years old, you can pick it up and throw it in the garbage. If it's 51 years old, you cannot touch it because it's a historical artifact. That's a kind of interesting little humor there. That's not made up humor. That's real life humor. Anyway, yeah, I'd like to introduce our speaker today. He's Ed Buie, and Ed is working with Professor Evans
Scanapiaco.
Thank you. I just have to say Evan all the time. Okay, at ASU, I'm investigating the role of turbulence in galactic halo simulations using computer simulations. And they predict many astrophysical processes, which are very important in our understanding of not only galaxy formation, but their impact on how the universe evolved after the Big Bang. And Ed's also very active in outreach and helping others. He's involved with efforts to improve the mental health of grad students and scientists in general by working to normalize and destigmatize mental health discussions in science and work. And Ed's a National Science Foundation Fellow, an adjunct faculty member at the Chandler Gilbert Community College, and also is an CC prison education teacher. So with that, please welcome Ed.
All right. Thanks, Tom. Thank you all for having me. Let's see here. Share my screen. All right. Okie dokie. So, hey everybody. Today I'm going to give a talk about turbulence and the halos of galaxies. And I got to thank the NSF for some of the simulation work that I'm going to be showing throughout this talk. In the background here is actually a picture from a simulation, not mine, from the Illustrious simulation. You probably have no idea what's going on, but that's okay, because by the end of it, you will at least have some clue of what's happening here. And so before getting into the talk, I want to acknowledge all those who have been negatively impacted by the COVID-19 pandemic. And thank you to all the essential workers for all of their efforts. And we all will get through this. So first, let's talk about some size scales of things, get us warmed up to the idea of where we're going. And so we're going to start with something we're all familiar with, the solar system, where we have the sun here, and then we have our planets, Mercury, Venus, Earth, Mars, got an asteroid belt with a bunch of rocks floating around it. And then we have the gas giants, Jupiter, Saturn, Uranus, Neptune, and all their moons. And here in this image is showing the relative size scales all the planets. And then outside of Neptune, we have what we call the Kuiper Belt, which has some more objects out there like Pluto, Charon, and actually the Voyager mission that we sent out many, many years ago. Um, and so if we look at, how big is the solar system, it's about 4.5 billion miles across, or radial distance. So half of it. And that's pretty big. And so astronomers, instead of saying 14.5 billion, we make up units for distances. So, it's easier to say where the distance between Earth and the sun, if we look at this uh, bar here, this is showing the relative distance scale. So Earth is right here, and the sun will be in the center. And this distance between Earth and the center is what is called an astronomical unit, or AU. And so the solar system is about 156 AU across. So it's pretty big, but we can get bigger, of course. And so the sun is not alone. We have many different stars that are kind of around our sun, and this is what we call the stellar region. Is about 15,000 times bigger. So this is getting into the trillions, tens of trillions of miles. And again, because astronomers, we don't feel like saying these big numbers all the time, and so make up another unit called the light year, where this is the distance light travels in 1 year, because light moves at a constant speed through space. And so this stellar region, with all our surrounding stars, our neighbors, is about 30 light years across. But of course, we can even get bigger than this, where now we want to look at what all this is in. It's in the Milky Way. And this is our sun here in a little circle here. But within, you know, outside of our sun, outside of our stellar region, we have all these other stars and whatnot around us, and we all reside in the Milky Way galaxy. This is an artist's rendition of the Milky Way galaxy. Of course, we're in it, and so we can't get a picture like we can't get a picture of the Milky Way from outside of it like this. But we have these spiral arms made of all the blue, all that blue light there, and all that blue light is actually young O and B type stars. These are very massive stars, tens of times bigger than our sun, and they don't live very long. They live fast and die young, and so they only live for about a few million years, up to maybe 10 million years or so. And just for context, the Earth and our sun has been around for about 4.5 billion years. Um, so we have these spiral arms, and then we have the center of the galaxy, and the center looks a lot different than the spiral arms themselves. Where in the spiral arms you see the blue light from those massive stars, but in the middle it's yellowish, reddish almost, and that's showing a different stellar population. So these are older stars mainly in the center. And the distance scale of the Milky Way is about 100,000 light years, so about 3,500 times bigger than the stellar region we were talking about before. And again, because astronomers, we make up units all the time. We don't feel like saying 100,000 light years or even bigger than that. And so make up a unit called kiloparsec. And so the Milky Way is about 30 kiloparsecs across. But of course, spiral Milky Way galaxy, spiral galaxy like a Milky Way, we can go even bigger than this. And so here I'm going to show a simulation where it's going to zoom in on different size scales, so you get the full range of distances that we're going to be talking about here. And initially, it's going to go through a few different. It's going to show different properties, and so it's going to start with this what we call dark matter density, where most of the universe is made of matter, but it's matter that doesn't interact with light, and so we call it dark matter. And we know it's there because we can feel its effects gravitationally. Scientists did some calculations many years ago, and were able to find out that if the Milky Way galaxy, if the amount of mass that we see in stars and gas is all the mass that's there, the Milky Way galaxy would have spun itself out many, many years ago. And so there has to be more mass there that's kind of keeping stuff contained for it to exist for how we see it now. And so that's kind of was some early evidence for dark matter. So I'm just going to play this video forward. And so it's going to zoom in, starts at this megaparsec. This is a million parsecs. And we zoom further and further in that web-like structure. Now it's going to the temperature, where bright red is really hot, and then the darker places are colder temperatures. So we're keep zooming in further and further, um, and we see uh, all these different blotches around. These are galaxies. Then we're zooming in further, and we're only looking at the stellar light. And so we see in the stellar light, obviously, the spiral got some stuff, puffy stuff around it, but everything else is pretty. It's just black. It's just dark. Um, and so you might think that, okay, there's not much else out there, it's just the stars and that's it. But if we instead look at the gas around the galaxy, and we see, oh, there's a lot more. It's all this green stuff around it, it's all this yellow out here, and each galaxy kind of has their own cloud of gas around it. And now it's zooming out away from that galaxy. We're back on the megaparsecs. So we're super far out from the galaxy. See all these different blue dots. Those are all different galaxies around there. And now this is a gas velocity. And so really bright yellow is fast moving gas, black is slow moving gas. And now we're back to dark matter density, or that dark matter web that we all are kind of in. And so that was a movie from the illustrious simulations. Highly recommend you check it out sometime. They're really cool. Um, but we're going to be talking about only a part of this stuff. And so we're not going to talk about the whole thing. We're going to talk about something called the circumgalactic medium. Uh, and so this was the gas that we saw around that central galaxy in the middle there. And circumgalactic medium, or CGM, I don't feel like saying, a name like that the whole time. So we're just going to call it halo of gas. Much easier to digest that way. And so this halo of gas is pretty big. It extends pretty big. We have galaxy in the middle. We can imagine, this is an artist rendition, by the way. And so this galaxy middle, we could say it's like the Milky Way galaxy, radius about 15 kiloparsecs. Um, and the full size scale of this halo of gas is 300 kiloparsecs. So it's about 20 times bigger than what we see in the galaxy, in the spiral galaxy itself. And there's a lot of stuff happening here. We have stuff like outflows. Remember, have those massive blue stars. When they die, they explode in these brilliant events called supernova that launch a bunch of energy and material, what we call metals. Metals being, astronomers call anything heavier than hydrogen, helium, a metal. So carbon, oxygen, iron, things that you traditionally think of metals, and things that you don't traditionally think of metals. We all call it a metal. So all that is launched out into this halo of gas, and it recycles already there, mixes up, and eventually it kind of rains back down onto the central galaxy. Um, and then we also have gas coming from outside of that halo of gas. We saw in that zoom out movie, there's a bunch of gas out there. It's not just in this halo. And so sometimes gas will feel the effects of the gravity from our dark matter halo around us, and it will attract that gas and spiral in or mix with the gas already in that halo. And then it's really diffused. So, for example, if we had a box of gas that was about a meter on each side, and we took this box of gas and we had it on Earth, and then we compared it with a box of gas in this halo, the Earth gas would be about a trillion times. There'd be a trillion times more particles in the Earth gas than in this halo gas. And so here, particles are super far apart. It's pretty hot. It's about 2 million degrees Fahrenheit. Uh, but even though stuff is really far apart, it's still, there's a lot of stuff happening here. There's a lot of interactions going on, and we want to learn more about how it evolves and how it gets this way. And so far, I talked about what's in it, these metals. So quickly, talk about atoms. We have electrons. These are negatively charged particles. They're pretty sad. Protons, they're positive charged particles. They're in the middle. They're happy. And the neutrons, they're just pretty chill. They're just kind of there, and they're in the middle. They don't have a charge. So the protons, neutrons are in this nucleus, and then you have around it are those electrons. But remember, this gas is super hot. There's radiation out in space. Sometimes particles collide, and if enough radiation hits one of these atoms with enough energy, or if things collide with enough energy, one of those electrons can come flying off. This is what we call a singly ionized atom. And of course, this can happen to more electrons. And so If another electron gets enough energy and leaves the atom, that's doubly ionized, and then triple, and so forth and so on. And so that halo of gas is made up of these different ionizations of atoms. We have some neutral, we have super hot gas, it's really ionized, missing its electrons, and it's all that there in this halo of gas. So how do we observe these halos? Well, to talk about that, we have to talk about something called quasars. These are, or active galactic nuclei. And so here I'm showing a picture of a galaxy on the far left, where immediately kind of notice these bright reddish, orange, yellow jets coming from the center. And they're bigger than the galaxy itself. This is taken with ground-based optical and radio data. Um, and so, that's pretty weird. So eventually years go by. And with the Hubble telescope, we can kind of zoom in on that center region, like, okay, what is causing these jets to come out? And we see this donut-shaped thing, and there's a little bright thing in the middle. And we look closer, and we know now that in all galaxies there exists a supermassive black hole, an object that is billions of times more massive than our sun. Black hole, an object that not even light can escape if it gets too close. And so what around it, we have what's called an accretion disk, and matter will fall into it. But sometimes not everything falls into it. Sometimes things don't get that close, and instead they get shot out in these beams of particles and energy. And that's what these are. These are this material that's getting shot out from that supermassive black hole that wasn't able to be um, fully sucked into it. And then, of course, we have the Event Horizon Telescope collaboration image of the actual supermassive black hole with this accretion disk. First time we were able to see a black hole. And so, using these, what I call universal lasers, because these are the brightest objects in the universe. And so, astronomers, we get pretty clever. We're like, all right, we can use that. And so that light goes through space, and on its way to us, it might interact with some halo of gas around a galaxy. If it does, then remember these halo of gas has a bunch of atoms in there. Those atoms will absorb some of that light. Some of those electrons might get flung off of those atoms because of that. But in this interaction, we can see these dips in what are called spectra. And we can see these dips and say, okay, so we know we can get an idea of how much gas is there along this line of sight. We can get an idea of what's in this gas as well, and what exactly is absorbing this gas as it goes from its source to us with the Hubble telescope or other instruments. Um, and so what I'm showing here is what that data looks like. This is showing neutral hydrogen, or H1. And there's been a ton of different surveys, halo surveys, that have looked looked at observations of this gas. And on this plot, I have the galaxy here. And so this is stuff close to the galaxy. And then as we move to the right, we're getting further and further away from the galaxy. And then on the y-axis, if you're up here, then it's a lot of absorption from hydrogen. If you're down here, then it's not a lot. And hydrogen is the most abundant element in the universe. So we expect for it to be a lot of hydrogen there. So whenever we want to look for something, we look for the hydrogen, because there's definitely going to be some hydrogen there. And we see that that neutral hydrogen is pretty much everywhere throughout the halo. It kind of falls off a little bit as we get really far out to 200 or so kiloparsecs. But we see it all the way through because there's so much hydrogen out there. Now, we can look at something else, something that's less abundant in the universe, magnesium. In this case, this is magnesium 2. And so this is magnesium with one of its electrons missing because it's been hit with energy or collided with another atom, and one of its electrons went away. Again, this is close to the galaxy, far away from the galaxy. And we see there's a lot of magnesium 2 close in to the galaxy. But as we move further out, we don't really see it there. So, okay, that's kind of giving us some clues of the structure of this halo of gas. And so we look at something hotter, something like oxygen 6. This is oxygen with 5 of its electrons gone. And in this case, it takes a lot of energy to remove electrons. And so if something is missing more electrons, then we tend to think that it is a hotter gas with more energy. And we see oxygen 6 not only in the middle, in the center, closer into the galaxy, but we also see it as we go further out. And so this kind of helps us to inform a mental picture of what this halo of gas looks like. Of course, these are observations, these like pencil beam observations through this halo of gas. And so we don't have a full picture. But with these observations, we're kind of able to get a sense of like, okay, this like we can imagine might be it's like fate, hazy fog almost of material with smaller clumps throughout that tend to be closer to the center, where those smaller clumps contain colder material. In this sense, when I say colder, it's still really hot when we're talking about Earth temperatures. But in the case of this, cold is about a couple tens of thousands degrees Fahrenheit, where super hot is millions. And so the magnesium 2 is kind of your colder material, and then your oxygen 6 is much hotter. So we have a situation with haze, clouds throughout. Well, okay, that's kind of similar to something that we know, Earth's atmosphere, where we have an atmosphere and then we have clouds throughout it that are colder than the atmosphere, where ice crystals and rain droplets can condense and form in those clouds to then rain material down onto Earth's surface. Uh, and so it's like, oh, that's really interesting. Something that exists really, around our galaxy is kind of similar, at least in a very extreme way, to Earth's atmosphere. Um, and so modeling helps us to understand how that halo evolves to get to what we see now, to inform the observations that we have. Because of course, this is happening over billions and billions of years. Human beings can't live that long. And so we're only getting clues from these observations. But with modeling, we're able to put in equations into computer programs and run this forward in time and see if we get similar data to what we observe in the universe. And with my research, Earth's atmosphere is a lot of turbulence happening, and so I wonder if turbulence can produce a similar halo that we, as far as observations go, around galaxy. But first, what is turbulence? So before COVID, um, when we were all riding on planes and whatnot, we might have experienced some turbulence like this on the plane, where the pilot might say, "Oh, we're hitting a rough patch of air. You want to buckle in." Is of course an extreme case, but the kind of turbulence I'm talking about is what's actually happening in that rough patch of air. And so this is these are random motions of particles where you have cold and hot air mixing, and that mixing uh, allows for energy to be transferred, and it ends up in a situation where you have all these particles and gas moving in random directions. And so that's what I'm talking about when I say turbulence. Keep this in mind, this stirring of uh, random motions. All right, cool. Well, let's simulate this. So we have a box. We take a box of some gas. That's what the red particles here. Then we shine some light on it. So, we just start pretty simple. We have a box of gas. We're just going to stir it up a bit, shine light on it. Remember those quasars or AGN. These are these lasers through space. They're everywhere. There's billions of galaxies. And so there's a lot of those. And there's a lot of radiation out there. And so we want to consider that. Uh, and so we go back to our halo gas example, and running simulations of this, we're able to see these are happening in a box, so in 3D, but what I'm showing here is a slice through the middle of that simulation. This is showing the neutral hydrogen. And so we're able to see kind of a snapshot of the whole picture with this. We see a lot of hydrogen sloshing around in the bright yellow, and then a very little bit of hydrogen in the dark purple, and then sloshing around, and it actually matches some observational data of what we see. But of course, this is only like a small snapshot of the whole thing, and we can do better than that. We can look at the whole thing. So why not? So we want to simulate actively star-forming galaxies. And what I'm showing here, this is M82. Famous galaxy has been observed a ton. And in red, you see a bunch of gas. This is material being ejected from that galaxy from all those supernova occurring within the galaxy disk. Remember, those blue stars, they don't last very long. And so when a galaxy is star forming, forming a bunch of stars, those blue stars are going to go supernova really fast in universal time scales. And so it's going to launch a bunch of material to that halo of gas. And so we want to understand the halo of gas around a galaxy like this. So we start with a box of gas, where here I'm showing slice through the middle. So we have a lot of stuff in the middle, and then not as much stuff further out. And then we start off pretty hot. It's about 2 million degrees Fahrenheit. And we stir it up and shine some light on it. And 3 billion years later, looks like this. It looks pretty different. We have these, we have kind of that hazy fog type situation we are talking about before, where with clouds throughout it and these tendrils, filaments of colder gas, and in the haze fog around those clouds, it tends to be much hotter. And so turbulence kind of sets up this flow in the halo, where hot gas is able to move out to the outer halo, recycle and mix with the gas already there, and eventually cool into these clouds and rain back down on the center. And of course, why show just a picture when we could show a movie? And so this is a movie of that simulation and how it evolves in time. This is showing the density, so the actual the gas, where the gas is, and then this is showing the temperature. And we have the size scale of the Milky Way disk here. And so you imagine the Milky Way disk would be in the center of this simulation, and you have that gas getting stirred up. And this is why, this is the power of simulations. This is a million years, and eventually goes to billion or giga years. And human beings can't live that long. But with simulations, we can see the whole picture kind of play out and how this gas might evolve in time. Yeah, I like making movies. It's always a cool thing we get to do. So this is pretty similar to, like I said, what we see on Earth, where we have an atmosphere kind of around it, and then we have these cooler clouds that kind of condense out of that hotter medium and rain material back onto the center galaxy. I'll just let it play for a little bit, because why not? We always like to see these movies happen. Yep. So how do different things compare? So first, I'm going to show neutral hydrogen. Remember, hydrogen, the most abundant element in the universe. This is at years, so at the end of that simulation. And then again, we have our size scale for the Milky Way in the center. And we'll see most of the neutral hydrogen, not surprisingly, is in the center. This is what we call tracing the cold gas. And we don't see it, so it's not a lot of it out here, but sometimes we see some clouds, some tendrils, and this is cooler material that's condensing towards the center. And instead, we look at something hotter, 5 times ionized oxygen. So oxygen with 5 of its electrons missing. It takes a lot of energy to do that. And so this is tracing the hot gas. And we see it's pretty much, no matter where you look, you're going to see it. And it's pretty much at the same level. It's not really much variance in this oxygen. And that's pretty similar to, remember, that mental picture we were kind of building up before with the observations of a haze of hotter material with kind of cooler clouds throughout it. And so we're going to, let's compare those to observations, where in the purple, I am showing the simulation data, and we have our Milky Way here. This is a lot of hydrogen, not a lot of hydrogen. And Milky Way is in the center as we move further away from the Milky Way. And we see these black squares from the Hubble observation data overlaps with, a good portion of the simulation data, being the purple bars. So it's pretty good. We look at the 5 times ionized oxygen. Um, there's less oxygen in the universe overall compared to hydrogen. Um, and yeah, but it still, it matches pretty well with the data. Not 100%, but it does a pretty good job of getting a situation similar to what the observations are showing. Um, so yeah, that's pretty good. So what's next? We use turbulence. We shine some light on it. Well, we think about, okay, what else is happening in these halo of gas? Uh, well, before we were saying, we're talking about the atoms. A lot of, there's a neutral stuff in there, but there's also a lot of ionized stuff missing with its electrons. And so if these atoms are missing their electrons, they're going to be more positively charged, where, the nucleus has the protons and neutrons, the protons giving that positive charge. And then electrons, of course, are negative. And so we have a bunch of positive and negative charges moving around. You're gonna have magnetic fields happening there. Uh, you all might be familiar with magnetic fields. Opposite charges attract, like charges repel. So positive will repel, but positive and negative will attract each other. So this is definitely going to be happening out there. And so we add in a magnetic field to what we already have, and see how things go. And so this is kind of the same simulation setup as before. The only difference is we added that magnetic field into it. And so I'm having some movies play on the bottom where density and then temperature and magnetic field. Um, and we see the same thing. The gas kind of expands outward, and eventually stuff is able to cool out of that hotter halo and condense in towards the middle. And then we look at the magnetic field. Um, we started off at kind of a uniform value, and then as that turbulence kicks in, magnetic fields, they don't like to be bent, and so when that happens, it generates a lot of energy. And so it's not surprising that where most of the matter is, that's where you're going to see, kind of the highest buildup of that magnetic field being present. But it's kind of throughout it. It almost looks like white noise in the outer halo. But something that, because of how these simulations are ran, something that happens in this situation is that in the center, stuff kind of builds up in the center, and it cools in towards the center. But we don't get that cycling that we saw before with just the turbulence when we didn't think about the magnetic fields. And that becomes more apparent if we look at just snapshots throughout that simulation time. So here I'm showing snapshots of, this is the neutral hydrogen at the top and then temperature at the bottom. So first, the 3 gigayears, we see, neutral hydrogen kind of throughout the halo like we saw before. It's pretty good. And then we go up to 3.5 billion years. We see little clouds of hydrogen. We see still some long filaments of neutral hydrogen. In the middle, still mostly hydrogen. But then we move on to 4.8 billion years later, uh, and it looks very different. We don't see these long filaments of neutral hydrogen anymore. We only see these little clouds, patches, and in the middle has a lot of hydrogen there, but outside we don't see the hydrogen that we saw before. And if you look at the temperature, we can kind of notice that this middle ring around the center is getting hotter and hotter, while the center of the simulation is building up of colder material, and we don't see that colder material far out anymore like we did before earlier, back in 3 gigayears or 3.8 or 3.9 gigayears. And so that magnetic field, what's happening is, as matter is cycling through, that getting stirred, hotter materials getting pushed out, eventually it cools, stuff cools back towards the center. That magnetic field is actually trapping colder material in the center, and it's not letting it cycle as well as it did before when we didn't consider the magnetic field. And so we compare that to observations, and it doesn't really agree with observations as we move forward in time. Where again, this is at 3 billion years, 3.9, and then 4.8 on the right. And this is showing neutral hydrogen. Purple is showing the simulation, and then the black squares are Hubble data. And then, we have the Milky Way galaxy again, being in the center as we move further out away from that Milky Way galaxy out to 250 kiloparsecs. And we look at 3 billion years. All right, we see some nice overlap with the data. The purple lines overlap with a lot of the black squares. So that's good. Move on to 3.9 billion years. It's like, okay, it's still it's overlapping with the data, but not as much as it did before. Definitely not as we move really far out. We don't see any hydrogen out here. Move to 4.8 billion years later. Oh, okay. All that hydrogen is pretty much in the center now. It's closer to the center, and we don't really see it outside so much, and it doesn't match with the data at all. Um, and so that's the point of simulations. We consider different physics, we add in different equations, we run it forward in time, and we always got to compare it to observations, because observations is what's reality, is what we see, and that's what we're trying to understand through these simulations. So all these simulations are cool, but how does this halo connect to the bigger picture? So what I'm going to show here is another movie from the illustrious simulations, except this one is the biggest scale stuff, and it's not going to zoom in this time. So in the top left is showing the starlight. You notice kind of these light patches here. That's where the galaxies are. And then the top right is showing the gas density. So this is where the gas is. Remember, if we, there's a lot more gas out there than there are stars. So we expect to see this haze and stuff where we don't see that in the starlight at all. This bottom left is showing the temperature, where your bright white and red is hot. Your green and blue is colder temperature. And then your bottom right is showing the gas metallicity. Remember those young blue stars, when they go supernova, they make metals and they launch those metals out into the halos of galaxies. Um, and so we're just gonna play this forward in time and see how the universe might have evolved. And so this is starting from way early on in the universe. We have these stars and small galaxies starting to come together in the starlight. And we see in the gas density this web of materials start to develop that we don't see at all in the starlight. And then temperature, everything's pretty cold still. And so as this moves forward in time, stars are going to be making their metals. And so you see more purple pop up here in this lower right panel. And gas, is doing what it does. It gets influenced by gravity and starts to come together. And so more gas is coming together. These galaxies are building up in size. Um, and if we look closely here in the temperature, you'll see small flickering start to happen. And those are this flickering are the active galactic nuclei um, turning on. Remember, as those supermassive black holes, they suck up material. The stuff that doesn't get eaten up is ejected out into the gas around it. And so that's what this flickering is. And things are getting hotter. Um, dense, gas is collapsing into on itself more. And now we're seeing these fireworks go off. These are the supernova happening, because all these stars are being made. And because so many stars are being made, a lot of those blue massive stars are getting made, and when they die, they go bang. And so they release tons of energy out into the medium around it, and all these metals get launched into the gas around it. Uh, and you see, this is not really a web structure so much anymore. Now it's like it's more like a hazy fog type of situation. And again, if we're looking at just the stars themselves, we wouldn't see any of that. We would just see the stars happening, but just the emptiness of space. We would think nothing else is there. But if we look at the gas and the temperature, look at all this action we'd be missing. And so, this is a simulation of how a part of the universe may have evolved in time. And this is pretty much taking into account like almost all your favorite physics that you might want to consider. So again, that was from the illustrious collaboration. See. So yeah, we learned a lot. We went on a long journey We learned about this invisible halo of gas surrounding galaxies called the circumgalactic medium. We learned that this halo is important to the central galaxy evolution. It's where gas is recycled. Gas flows outward and inward. The gas that flows inward kind of helps to fuel that star formation, which is really important because we see galaxies forming stars now, like our Milky Way. Um, all these processes that mix, the outflows and the inflows, they all mix hot and cold gas together, and that leads to turbulence. And when we consider turbulence as well as, just shining a light on that halo, it gets us closer to understanding the observations, to understanding, how this halo of gas even evolved to what we see now. We also saw magnetic fields do weird things. Depending on how we think about the magnetic field and what equations we use to consider that magnetic field, the matter will do weird things with it, and we may not get a situation like reality. Um, and then we learned that this halo connects the central galaxy to the rest of the universe. In the end, everything is connected. It's just a matter of what scale you want to look at. Uh, and so, yeah, thank you. That's all I got.
Great, thank you, Ed.
Yep.
We've got a couple questions. Let me see if I can let the person asking the question ask it live if they wish to. Let's see if I can do that. Oh, where did he go?
So,
Are there parts?
yes, my question is this. What are the driving force for this turbulence? Is it happening in all the galaxies?
Okay, yeah, that's a good question. So the driving force for this turbulence is pretty much just the injection of energy. Like I said, these gas is moving. That's gonna that takes a lot of energy to move gas around. Stars are being formed. Stars are going supernova. That releases a lot of energy into the medium around it. And so all those processes, gas flowing just randomly, as long as, in addition to those supernova going off, is what drives that turbulence. And yeah, it's happening all over. We look at anywhere in space, we see turbulence. It's just at different levels, depending on where we look.
Okay, thank you. Sasha, would you like to ask your question?
Yeah, so in the videos that you showed in one of the last few slides, you said the bottom left was the temperature scale. I was just wondering what, I guess, what was the variance in temperature?
Oh, that's a good question. I don't know for sure, but I would imagine it is from a couple million degrees Fahrenheit to a couple thousand degrees Fahrenheit.
That's a lot more
Yeah.
temperature than I was thinking about.
Yeah, definitely. But yeah, these simulations, they are like these are simulations that got me to want to simulate stuff. And they are super high resolution, and they pretty much have like all the physics in there. And so I can't imagine how long it takes to run them. It must be months.
All right. Well, thank you.
Yep.
Okay, and Henry has a question, if you'd like to ask it, Henry.
Yeah, hi.
Hello.
Is the percent dark matter in a CGM roughly the same as it is most other places in the universe, or does it vary, or what's your take on that?
Oh yeah, that's a good question. Um, hmm, where's about that? I would say it is. I mean, it's definitely. It depends on where you look in the universe.
Right.
Um, because like what we see here, this web-like structure, there's going to be more dark matter along that web-like structure. Um, and so when we're talking about like in the circumgalactic medium, yes, and then within the galaxy, yes, the ratio is about the same. There's a lot more dark matter compared to regular matter. But there have been galaxies found in these places called voids where we don't, it seems like there isn't much dark matter out there, but we still see like regular matter like we're all made of. Um, and so that's still something that we're trying to understand. But when we're talking about the circumgalactic medium and then in the galaxy, yeah, I would say the ratios are pretty much the same.
Okay. I had another one if I have time, Tom.
Sure, go
Um,
ahead, Henry.
How much mass of if you count the galaxy and CGM and everything, how much mass is in the CGM versus the whole galaxy? Say for a spiral like the Milky Way, are we talking 50% the mass in the CGM, 60, 20?
Mm-hmm. That's a good question. It is definitely there's much more mass in the CGM than there is in the galaxy. I
Okay.
don't know the percentage off the top of my head, but I want to say at least like 70%, probably more in the CGM than compared to the galaxy. So like most of the mass is in the CGM, not in the
Okay.
galaxy itself.
That's what I was thinking.
Yeah.
Another question: can the CGM, with all the mass and so far and how far it extends on each galaxy, help with the missing baryonic mass problem?
Yes, yes, yeah, that's a good question. Yeah, definitely. That's actually like that's happening now. This he's getting better observations of the CGM is helping to kind of fill up the amount of count up the amount of baryons that we think are missing, and so uh, they may not be missing anymore, but that's still happening now.
One last thing is I noticed on your supernova, quad picture here, the
Mhm.
explosions look pretty big to scale. I just was
Yeah.
wondering if that was, artistic effect or what.
Oh no, that's real. So
Hmm.
um so remember these, these blue stars, a lot of them are born at once and they all kind of live to about the same age. And so when they go supernova, pretty much all of them do. And so it's going to
Okay.
release these huge shock waves. And so that's why they're so big. It's because tons of them are going off at once.
Right. Okay. Thank you.
Oh,
Yep.
wow. You want to steer clear of that, I'd say.
Yeah, definitely.
Okay, then Thomas Harvey. Let's see if I can you access your mic, Tom? Maybe not. So he had a question. How does your work relate to the Fermi bubble of the Milky Way? And maybe explain what the Fermi bubble is. I haven't heard of the Fermi bubble personally.
Yeah. So I've heard of the Fermi bubble before, but I don't remember off the top of my head what it is exactly. But I feel like it relates to what is it? Just some sort of like galactic outflows happening that's releasing a lot of energy to the halo, and um, but I feel like that has I feel like that has a lot to do with the radiation being released from the galaxy. And it's my simulations with turbulence is kind of on a more on a general sense of, okay, I'm just gonna put in some energy. I'm not gonna worry about where the energy source is. And so in reality, the energy source could be, from stars going supernova or AGN activity launching those jets out, or just radiation light from that galaxy. Uh, and I want to see how that energy injection affects the matter in that halo. And so it's kind of related, but the Fermi bubble is like a particular source of that energy, where the turbulence is just I'm just putting in energy. I'm not really worrying about its source.
Thanks.
Okay. Let's see. See, Tom Curry, he doesn't have a microphone, but he was wondering what keeps the halos from temperature dissipation into the colder part of the non-galaxy part of space. So why does the center get cold?
Yeah. Okay. Yeah, that's a good question. So first of all, it's the halo is hot because it's in because it has gravitational energy. And because it has this energy, it's going to be at a certain temperature, depending on how much mass is there. And most of the mass is in dark matter. So that temperature happens to be around 2 million Kelvin for that size scale of a galaxy. Um, and what happens is eventually that gas will, those particles will release energy. And as it does that, it will cool. And so as it gets rid of some energy, gas is going to cool and it's going to start to clump together in those clouds. And this is just, this is just the nature of gas. It's just what it does. It likes to cool. There's all those different elements, and they want to release energy. They want to get back to being neutral. Want to capture their electrons again. And gravity always attracts things to the center of mass, and so stuff tends to cool towards that center where the galaxy is. Oh, Tom, you're muted.
Thanks, Ed. Let's see, back to Paras. Do you want to ask your second question?
Yes. In your model, how do you simulate time, like billions of years? Do you just have to run the model for longer, or do you have to change some other parameters?
Yeah, that's a good question. So pretty much we just run it for longer. The simulations I showed, it took a couple weeks, almost a month or so, a little bit less than a month. But in the simulation time, like every second is a couple thousand years. So, supercomputers run things much faster than I can run them.
Thank you.
So
Great
just
talk.
Thank you.
just by letting them run, you scale that run
Yeah.
time. Sasha has another question. Go ahead, Sasha.
Yeah, I was just wondering, I mean, if your simulations take a long time and obviously you're doing a lot of work, but how many nodes do you normally request for these simulations in addition to how long it takes?
Okay. I request.
Maybe explain the nodes too for everyone else.
Yeah. So on the supercomputer, really on all computers, they all have processors. Oh man, it's been a while since I really thought about it in terms like this. But they all have processors. Those processors have cores. Sometimes a laptop might be 4 cores or something. That's pretty much a measure of its processing power. So, and processors is or cores is another name for nodes, or process is another name for nodes. I forget which is which, but the more nodes you use, the more computing power you're using. And that's pretty much the base of it. And so I am using, I think like 32 nodes. Yeah, 32 nodes. And each node has it has a maximum amount of processors to it, like 72 or so. And so on 30 some nodes, I use maybe 60 some processors. And so it ends up being almost 1,000 or so total processors that I'm running these on. Yeah. So
Wow.
it's a lot. Definitely more than my laptop. My laptop is maybe like 4 or so. But you could always do way more because you can run on hundreds of nodes.
Okay, thanks. Let's see. I spotted a couple questions in the chat. One from Brooks, our treasurer. Thank you, Brooks, for being treasurer. But he asked, for the gas cooling, where does the lost energy go?
Oh, yeah, good question. The lost energy goes to the halo around it. Energy is not created, destroyed, just kind changes form. And so that energy, you might, those, as stuff cools, it might release a photon. And so that photon of light leaves electron might meet an atom, stick to it, a light photon gets released, and then that photon is just out into the halo and might hit another atom out there. And so, yeah, that's where that energy goes. Just kind of keeps that halo hot.
Yeah, I think you were mentioning outside of this central region, you had sort of a ring that was a little bit hotter.
Mm-hmm.
So maybe that's where some of it goes, I think you're saying.
Yeah.
Okay, then Henry put another one in the chat. How does the size mass of a CGM compare with spirals, ellipticals, and dwarfs? And CGM is what, the cool galactic medium?
Mm-hmm. Okay. So typically, your dwarf galaxies, those are your smallest galaxies. And then spirals usually are like the next biggest, and then ellipticals are usually the biggest galaxies you'll find in the universe. Your elliptical galaxies, they don't have spiral arms. They're not forming new stars like spirals are. Some people call them red and dead galaxies because they typically are red or yellowish. They're mainly older stars, and may be formed from the merging of two or more spiral or dwarf galaxies. And so the CGM of an elliptical galaxy is definitely more massive than that of a spiral usually, and then definitely that's more massive than one of a dwarf. The dwarf galaxy has the smallest CGM.
Okay, I think that does it for questions. Let me make sure. Oh, one more. Sorry, Bill. Let me see if I can get you to ask your question by yourself, or to find my screen. There you go. Go ahead, Bill. Ask your question. Oh, well.
Can you hear me now?
Yeah, we can hear you now.
Okay. My question is what percent of the mass of a galaxy that is non-radiating, non-glowing regular matter in a galaxy that is not dark matter? What percentage of mass in the average galaxy that is non-radiating, non-glowing regular matter?
Very small, like like in the 1% or so, like in the just single digits.
Why wouldn't most matter be non-formed into stars and massive gas clouds?
Just because, so like I said before, most of the gas in a galaxy is in the CGM, and it's really hot. Stuff is really far apart, and because stuff is so far apart, it's harder to cool, and so it kind of just stays in that hot phase and where most of the mass already is. But as time goes forward, eventually some parts are able to come together, able to cool, and that's when you get your clouds, and then they go towards the center, and that's when you have more cold gas that's able to eventually go on to form stars. So I hope that answered your question.
Yes, thank you.
Okay.
Yep. It sounds like cooling is a lot harder than it sounds.
Yes. Yeah.
Yeah. Okay. Let's see it. Okay, that was it. So thank you very much, Ed. It's very informative. I'll turn the meeting back over to Gordon. Let Gordon wrap up.
All right. Thanks for having me.
All right. Yeah. Ed, thanks a lot for a subject that most of us didn't even know existed, and you making it fascinating and understandable at the same time. So thank you very much. And it's just another example of the great presentations that we give here with the East Valley Astronomy Club meetings. and we are certainly going to continue these into next year. And let's see, on the, at the end of this month, I'm going to be partying like it's 1999. It may be by myself, but like I said, let's get this year over with. Next year is promising. These things that we've come up with this year, like the online events that we have, will continue next week and build upon what we were doing before. So our club is going to grow to next year. So keep those dues coming on in, and we can make sure that all the bills will be paid, and we can keep these great presentations by the industry's leading professionals like Ed here, keep them going. Our next meeting is on Friday, January the 15th, and that's about the composite images that our professional observatories are doing. Just like some of us are stacking different frequencies of light to make our images, well, the professional observatories are doing the same thing with their instruments. Remember the conjunction on Monday. Now, just don't go running out there on Monday and figure, oh, wow, there it is, there it is. I mean, the next few days is go ahead and look, and you can see how dynamic the universe is just with your eyes. I mean, how the stars appear to be motionless. We have two objects that have been coming closer and closer and closer together. It's kind of more like this. So take a look, especially before it starts getting cloudy out there in the next few days, and look towards the southwest, pretty low in the horizon. And so after the conjunction, we're only going to have a few more days and it'll disappear during sunset. So take a look at the conjunction. Dues, remember guys, dues are due, and help keeping your club going through next year. That is it that I have. Everybody who joined us tonight, thank you. And Ed, thanks again. What a fascinating subject. That's something that we don't hear much about, that's for sure. So what I'll do is, Tom, is there anything you wanted to add?
No, just to reinforce what you said, Gordon, don't wait till Monday to look. Monday might be cloudy. Tomorrow's gorgeous. Sunday will be gorgeous. They're supposed to be clear. You know, get your telescope out, at the very least binoculars. But I think it looks the most impressive in a small telescope. So
Yep.
Get out there.
Yep, and there's a lot of people out there that have bought telescopes in the last few months during all these lockdowns. So what's impressive, what has been impressive, is how these two objects are getting closer and closer together night by night. So that's been fascinating to watch through the month. So, okay, guys, I will give my usual countdown, and we'll end this month's general meeting. 3, 2, 1. Thanks, everybody, for joining us.